What's going on, everybody? It's Mr. Gustin. I'm back in the physics classroom. Today is not so much a lesson as much as it is an example problem. So I've got an example problem here. We've been discussing conservation of energy, and here's actually going to be a pretty cool example of conservation of energy and the work energy theorem happening simultaneously. We'll look for different points in which energy is conserved, or mechanical energy is conserved, and different points in which mechanical energy may be dissipated into thermal energy because of friction. So this is what we're going to look at. Before I even start this problem, let's look to see where friction works, where friction doesn't work, what my system might need to be in order for us to have a conservation statement that works. And you know, what forces and things might be outside my system. So here's my example, or my problem, my scenario. I've got a block, and it has initial velocity at point A. It slides across a frictionless surface, down this frictionless curved incline, up this frictionless curved incline to point C, and eventually reaches a friction full spot and travels a distance of D before it comes to a rest at location capital D. So if I've been thinking about this and I want to choose an appropriate system, there's probably two systems I could choose, but certainly one makes this easier, I think. It makes it easier for me to understand, perhaps, and keeps energy conserved rather than needing to rely on the force of gravity to figure out work of gravity. So I'm going to choose to include gravitational potential energy in my system, and therefore make my system the Earth and box. Both of these are going to be in my system, so I have available to me the energy of kinetic energy and potential energy between the lowest point in my system and where the object is. And so I am actually going to call this down here 0 UG. I'm going to say down here is the lowest point in my system because I'm near the surface of the Earth. I can do that, and I can discuss the changes in potential energy. So that's the plan there, okay? And I've got two questions. The first question I want is to find the speed at B and then find distance D. I want to find both of those values. And before I do that, I want to kind of figure out where is energy conserved and where is energy not conserved. So where are the outside forces? So as I think about this, I think about the initial energy A. The energy at A, we'll just call it EA for now. From A to B, are there any forces that are outside acting on the Earth box system? Well, there's gravity that pulls it down this incline, this curved incline, but there is not friction because it says the coefficient of friction is 0 on this smooth surface. So the energy at A, there is no force that would cause a change in energy or a force that would do work on this system. So that means all of the energy or mechanical energy at A is equal to the mechanical energy at B. We have conservation from A to B. Let's look at C. From B to C, and C is just at the very height of this curved surface. Again, frictionless, the coefficient of friction is 0. So from B to C, there is gravity, the force of gravity acting on the box Earth, or acting within the box Earth system, which causes energy to transform, but it doesn't cause energy to change, which means that the energy at point C is also equal to B and to A. If I think about point D, does D also have energy equal to these things? And the answer is not exactly, because from C to D, there is an outside force. The surface produces a force with the box, we call it friction, and it removes mechanical energy from my system. It creates thermal energy. It brings this box to a stop. So that means that the energy at D is actually not equal to the three other energies. So we can't include that in our conservation statement. We'll have to make some kind of work energy statement when we get there. But for now, I'm not so concerned about point D because question 1 asks me to find the speed, or V, at point B. That's what this asks me. So let's go ahead and borrow from energy statement A, energy statement E. Let's use both of those locations since that's what I'm concerned with over here. Energy at A equals energy at B. Let's track the energies that are present. First question, at A, is the box moving? And the answer is yeah, it's moving. There's kinetic energy at A. At A, is the box above the lowest point in the system? It is. That means there must be also gravitational potential energy at A. This is the energy present there. at point B, let's ask ourselves these questions. Will the box be moving at B? Well, it asks me to find the speed, so probably. And it's clearly gone down a hill. So there is kinetic energy at B. Is the box above the lowest point in my system at B? The answer is no, it is at the lowest point in my system. So there is no UG. Here is my energy expression. Ka plus UGA is equal to the kinetic energy at B. All of that potential energy from A is now converted, transformed by the internal force of gravity into the kinetic energy at B. I'm going to need some information. I'm going to actually start solving this now. So I got 1/2 mva squared. And notice, it's important that I say speed at A, because there is a speed at B, and they are different values. If I go ahead and just call it V, I might accidentally algebraically drop something out that does not drop out. So we don't want to do that. Plus UGA, which is going to be mass times G times the height at A, and that's going to equal 1/2 m velocity at B squared, and this is what I'm solving for. Remember, I'm looking for the speed at point B. That's what question 1 asks. The first thing I see that algebraically drops out is mass. I don't really care, or at least the speed of this object is not dictated by the mass of the object. The only force speeding up is gravity, and gravity will speed things up regardless of their mass. So I drop that out. I get 1/2 the speed at A squared plus G, the height at A, equals 1/2 speed at B squared. I know the height of A is 3 meters. It's on my picture. I'm going to refer back to see if maybe my example problem in our packet gave me an initial speed. It should have. It must have. I sure hope it did. It does. Give me 1 second here. The initial speed of this block is 6.3. The initial speed is 6.3 meters per second. It tells me this. So I go ahead and I start plugging these numbers in. 1/2 6.3 meters per second squared plus baby G times the 3.0 meters I have at the height at point A. This is going to be equal to 1/2 VB squared. And so all I would have to do there, bring the 2 over it, take the square root. What I end up having is 6.3 meters per second, this quantity squared, plus 2g, because the 2, I bring the 2 over, the 1/2 over, it gets rid of this, but throws a 2 in front of here, times 3.0 meters, and the square root of all of this will give me the velocity, or the speed, it will give me the speed at point B. Pause your video, calculate this, I will give you my answer. I end up with 9.92 for the speed at B. What is the speed at B? 9.92 meters per second. How do I know that? Because I use my conservation of energy expression. Okay? Question 1, solved. Question 2 asks find D. Question 2 says the distance over that rough patch equals what? And now I need to choose. I need to choose a section, right? Energy at A, energy at B, energy at C, all of those are equal. And I know that all of that energy eventually is going to come to a stop, right? There's going to be work done that brings this thing to a stop at point D. So I'm going to go ahead and choose probably choose point A, just because we've already used point A. So let's go ahead and use point A. We'll copy that down. We'll say the energy over here, the energy at A, which is equal to B, which is equal to C. It doesn't matter because the value is the same even though the types of energy are different. So the energy at A is the initial energy. Is there work done on my system? And the answer is yes. Over this path, there is certainly work done on my system because there is an outside force of friction. So there is work done by the force of friction kinetic. Lastly, is there any energy stored in the box Earth system? This is tricky. There's no energy in the box alone. The box comes to a rest. But is the box, even though it's stopped, is the box still above the lowest point in my system? And the answer is heck yeah. It's all the way up here. So there still is energy. And in fact, there is energy at D. And that energy is the gravitational potential energy at D. Over here we have kinetic energy at A plus the potential energy from gravity at A minus, because force of friction and distance are opposite directions. Now we throw the minus in there because the dot product of those vectors, we know it will take work away. So I'm left with this energy expression. Ka plus Ug minus the work of friction will equal whatever potential energy is still there at point D, because the box and Earth system is separated. They are separate. There's a separation between box and Earth. Therefore, there's gravitational potential energy. Let's start figuring some stuff out. Over here, I know exactly what my energy is. mv squared plus mgh. We've solved for this. This is at A. This is at A. Minus the force of friction. Do I know what the force of friction is? The answer is no. I don't know what the force of friction is. But when the box is on this surface, Fg is balanced with Fn. These are equal, so the normal force is my weight force. Friction, as you remember, is equal to, kinetic friction equal to the normal force times the coefficient of friction. If the normal force is balanced by gravity, I can make the force of friction be equal to mg mu k, but I cannot forget to multiply it by that distance value. And then the potential energy is mg at point D. What I notice again here is that all of these terms have mass in it. I can remove those masses. Apparently mass does not impact this final answer. It does not impact the distance this thing takes to stop. So 1/2 speed at A squared plus g, the height at A, minus g times the coefficient of kinetic friction times that distance value I'm solving for is equal to g times the height at D. Let's go ahead and solve this problem. I might isolate D first, plug some numbers in. You can pause it here, use your numbers and solve once I tell you this. Once I tell you this height is 1.5 meters. Now you should be able to solve this problem. I'm going to work here. You pause it. You do your work. You come back. You check in on me. You come back. I forgot to give you that number. You need that number. Okay, if you're back, Sorry, I forgot to give what the coefficient of kinetic friction was, and it is 0.2. 0.2 is the coefficient of kinetic friction. Now that you know that, go solve it. Or, wait a second, here's what I got. I got 2.625, 2.63, around there, as the distance this thing will take to stop. So what is the distance? 2.63 meters right here. This is what I get when I go ahead and plug in the speed at A, the height at A, the height at D, which is a tricky number because even though H is 1.5, it's still 3 plus 1.5 meters above the lowest point in my system. So be sure to use 4.5 for the height at D. I use G again in the denominator. Those G's don't cancel out, so don't cancel those G's out. Not every term has a G in it, so I can't cancel G's out algebraically. And then obviously, I forgot to give you that 0.2 for the coefficient of kinetic friction. Solving all this, I have now solved for the distance at the top of this little smooth surface and then rough patch where we bring this box to a stop. This is us using conservation of energy in the beginning between 2 points where there are no outside forces to determine some value. And over here, question 2 is us using the work energy theorem to determine how much work is done on a system when there is an outside force causing changes in energy. As always, if you have questions, you may drop it in the comments, you may email me, or ask me in class. Until next time, see ya!